Hi everyone, my talk is about my recent project, Generate Your Neural Signals from My Individual-to-Individual EEG Converters. As we know that models in cognitive neuroscience or computational neuroscience trained on one subject are hard to generalize to other subjects because of individual differences. Neural activity varies greatly from individual to individual. So is it possible to overcome this challenge for neural signals? There are some previous methods to overcome it. The first one is anatomical alignment. We also call it normalization. So we can align different individuals' brain to a common template. However, using this method, we cannot align the functional topography across individuals' will. And this method is not feasible for low spatial resolution recordings, such as EEG. Another method called functional alignment, we also call it anatomy-free method. So we can construct a common space of neural representations across different individuals. And based on this common space, we can predict the neural signal of a specific subject. However, this method needs a large number of subjects to obtain an accurate common space. Also, this method can only be used for fMRI signals because for EEG, the spatial locations of EEG channels across sessions and subjects are not as stable as MRI voxels. So is there any other more flexible way to address these limitations? Yes, we can use individual-to-individual EEG converters. For example, we have two subjects and we have the neural signal of subject A. We can input the signal into a neural converter and it can generate neural signal of subject B. Previous study has applied this method to fMRI studies. They propose linear fMRI inter-individual converters. So based on this neural converter, you just need to input fMRI activity of a source subject, and the converter can output to predict the fMRI activity of the target subject. And this method can reach higher than 50% conversion accuracy. So the goal of our study is to construct high-performance inter-individual EEG converters. And here's the outline of my talk. First, I will introduce the dataset we use. Then I will introduce the linear EEG converter. Then I will introduce our EEG2EEG converters with very high performance. At the end, I also introduce some evaluations results on EEG2EEG models. First, for the dataset we use, here we use THINS EEG2 dataset. In this dataset, we had 9 subjects. Each of them did a visual perception test, and we used 70 channels from occipital and parietal areas. There are 2 sets, training sets and test sets. The images in these 2 sets are not overlapped. And we focus on a time window from stimuli onset to 200 milliseconds after onset, corresponding to 200 time points. Then we use the linear EEG converter to generate EEG signal from one subject to another. So based on this, we hope we can input the EEG signal from subject A to the linear converter, and it can generate EEG signal from subject B. Here's the example of the EEG signal of 2 subjects they viewed same birthday cake images. The shape of the signal is 17 channels by 200 time points, so we have 3,400 features in total for each trio of each subject. Then we want to train the linear converter to learn the mapping from 3,400 features of subject A to 3,400 features of subject B. And based on this, we can test the performance. Here's the example. The orange lines correspond to generated EEG signal and blue line correspond to real signals. You can see the performance of the linear EEG converter is okay, but these 2 lines are still not very similar to each other. So can we improve the performance of the EEG converter? We have some inspirations from computer vision. In computer vision, there's a model called UNet. It can reach very high performance in image segmentation. And there are some applications of the UNet, like the 3D UNet. You just need to input a 2D images and it can generate 3D objects. Also, a very famous application of UNet is pixel to pixel. In this model, UNet serves as a generator and it can generate images from one style to another style. So based on this, we are thinking about whether we can make a model have very similar structure that we input the neural signal of subject A and it can output the neural signal of subject B. So we build our EEG2EEG converters. For our EEG2EEG converter, the input is the neural signal of subject A, the output is the neural signal from subject B. And you can see the structure of EEG2EEG is very similar to UNet. It has UNet-like structure, including some early connections across convolutional layers. But here we just use 1D convolution because we don't have very strong assumption of the relationship between different channels. So for EEG2EEG, we want to input real EEG signal from subject A, and it can generate EEG signal from subject B, and we compare it with the real EEG signal from subject B. The difference between these two is the loss. And for the loss function here, we have two components. One is MSE loss. For MSE loss, we want our generated EEG signal has very similar amplitude as the real signal. And the second part, the CogSci loss, we want to use this to make our generated signal have very similar spatial temporal patterns as the real EEG signals. Then we can train our EEG2EEG converters. Here's a single image demo. We have the real EEG signal of these two subjects when they viewed the birthday cake images. And we can input the neural signal of subject 8 to the EEG2EEG converter, and it can generate neural signal of the subject 3. You can see here, generated EEG signal are very close to the real EEG signals. Also, there are some other examples from a subject to another subject. And you can see the generated result is very similar to the real result. We also quantify the EEG2EEG conversion performance. We calculate the overall correlation between real and generated signals to get the generated accuracy. Because we have 9 subjects, so we trained 72 different EEG2EEG models from one subject to another. And here's all the models results. You can see all the models can reach very high performance, higher than 50% conversion accuracy. So is the current EEG2EEG model the best? Because in this structure, there are two very important components. One is early connections across convolutional layers. The second one is compared with traditional MSE loss, we add a CogSci loss function here. So we did ablation experiments. We trained some other models, like the linear model, the EEG2EEG model without early connection, EEG2EEG model without CogSci loss function. However, we find our EEG2EEG model is the best. So both early connection and CogSci loss function can improve the performance of the EEG2EEG converter. So we need both components. In summary, our EEG2EEG converters can reach very high conversion performance of EEG signals from one single subject to another. Then we also did some evaluations on our EEG2EEG models. First, we asked what can influence the generated accuracy of EEG2EEG. So we did some correlation analysis. We calculate the correlation between generated accuracy from subject A to subject B and generated accuracy from subject B to subject A. We also calculate the correlation between generated accuracy and the original EEG similarity between two subjects. Also, we calculate the correlation between generated accuracy and the EEG variability of the source subject or of the target subject. However, we only find a significant correlation between generated accuracy and EEG variability of the target subject. This suggests that generated performance based on EEG2EEG is only influenced by target subject's EEG variability. Another question is, we have very similar generated results, but does this similar generated data also contain as much visual information as real data? So we did information representations analysis. We used two methods. One is classification-based decoding. The other one is representational similarity analysis. We did both analysis based on real signal and generated signals. First, for the EEG decoding, we want to track the representational differences between images. So on the left is the result based on real data. We find a significant time window of representational differences across different images. And on the right is the result based on generated data. It also showed a significant representational differences of the pattern across different images. Then we did EEG representational similarity analysis to track visual representations in neural signals. First, we input 200 images into a deep convolutional neural network, AlexNet, and we get the features corresponds to different layers, and we compare these features corresponding to different level of visual information with our real neural signals or the generated neural signals. And we want to see how these neural signals represent different level of visual information. On the left is the RSA result based on real data. We find a hierarchical representational similarity patterns between real data and the CNN. This is consistent with previous studies. And on the right, based on generated data, we also find this hierarchical representational similarity results. And even the similarity between generated data and the CNN is higher than the similarity results based on real data. So for here, we find generated data based on EEG2EEG contains sufficient visual information. Better EEG decoding and RSA results of generated data suggest that EEG2EEG can not only convert visual information from individual to individual, but also denoise the EEG signals. Finally, we want to ask how many training samples are enough. So we trained EEG2EEG model with partial data. And the result shows that generated accuracy could be higher than 65% when we just use 12,000 samples. However, it looks like more samples could result better performance. So in summary, this is the first flexible EEG converter that can reach very high conversion performance from one single subject to another. And the EEG converter is designed based on nonlinear full convolutional layer-based U-Net-like model called EEG2EEG. EEG2EEG can effectively generate realistic EEG signals for previously unseen visual images. And also generated EEG signals based on EEG2EEG contain sufficient and effective visual information, and the EEG2EEG even embodies a certain ability of signal denoising. Thanks for listening, and you can find the codes of EEG2EEG on GitHub website and our paper of EEG2EEG on arXiv.